Cinderella, how was your date?
It was terrible. We broke up already.
What happened?
He told me he preferred Elsa.
Let it go, let it go.
Oh no.
And I found out that your magic is fake. It's actually just an indicator.
Oh,
Can you tell me how it works?
okay.
Hi.
Hello. We are
normal
normal.
again. Yeah. So now, before we move on to discuss the titration curve, I think we need to do a little bit of groundwork first.
Yes.
So, William, would you like to discuss this?
Yes, alright guys, to really help you in the process of titration curve, which is really a very big struggle for most students, okay, I'm going to need you guys to take out the summary sheet that was given to you, right? So over there is what we call this situations that you encounter in acid-base equilibrium. Now the whole point is you must be aware there are 4 big situations we'll encounter in this chapter, and your job is to identify the situations and then be able to apply the correct method to solve for the question, right? So we just quickly go through whatever we have done across the past 3 weeks, right? I think we started off by teaching the students what are examples of strong acids, strong bases, and the key thing about strong acids, strong bases is what?
They're going to fully dissociate.
Yes, right, it's really the degree of dissociation. You expect to see a full arrow. So every time there is a strong acid and strong base, you just simply apply the formula, negative log H plus or OH minus, right? We then went on with the discussion of a weak acid as well as weak bases, and what's the difference?
It's going to dissociate partially now.
Yep, you're right. So right over here, we have a partial dissociation. And what is distinctive about weak acid and weak bases? We always look for things, you know, like Ka as well as Kb. Now, the methods will differ slightly. There are 2 ways to do it. You can either be using the ice table and you write down the Ka expression to solve for the H plus concentration, or you want to use like a mini shortcut, you can simply apply this particular formula. We have talked about this before. H plus concentration is square root Ka times C. And you can do the same thing if you know that this is a basic salt, but then you'll be calculating concentration of OH minus.
That's right. So to consolidate, if you are still not quite sure what's going on, you can always refer to page 55 for the notes, just to review a little bit on what's going on. So let us just start to number all these kind of different scenarios. So I'm going to call this scenario number 1, a strong reagent. This is going to be scenario number 2, a weak reagent. And the third scenario is going to be a salt. So if the solution only contains a salt, remember the most important thing that you should do is to identify whether if the salt is acidic, basic, or neutral. Now, neutral is going to be easy because the pH is definitely going to be 7. But in the event that you have an acidic or a basic salt, then we're going to use different methods. So once again, I'm going to provide you with 2 different methods. These methods are similar to that of the weak reagent, right? So for method 1, apply the ice table. But the special thing when I try to include the acid dissociation constant is that I must make use of Kw to perform the calculation. But after that, subsequently, the methods will all usually be the same. Right?
Yes.
We can also make use of the shortcut again, right?
Yep.
You can also make use of the square root formula, but of course, you still need to use the Kw expression to help me to find out the Ka.
Yeah.
So
Just remember, like acidic salt must have Ka, right?
Yes.
Basic salt must have Kb. Just remember that.
That's right. So I think you can also make use of the same ideas for the basic salt as well. So in the event that you cannot remember how to do this calculation, feel free to refer back to page 59 of your encyclopedia. That is where you can review before going on for the next video. Okay. Now, the last scenario, which I call this scenario number 4, is where we get a buffer. And under what situations would you see a buffer?
Buffer must have a conjugate base pair.
Yes, it must be a conjugate acid-base pair. So depending on whether it's an acidic or a basic buffer, the formula to use are over here. You do realize that the 2 formulas all depend on the ratio between the 2 major components of a buffer, its weak acid or base and its own conjugate.
That's right.
So now, I think we can finally go on with titration curves.
Yes, all right. Now, in your encyclopedia, you will notice that there are 4 different types of titration curve. We're just going to spend time today, right, on just one of them. We're going to go into details. The other 3 is going to be covered by our teachers in class, all right? Now, if you take a look at your notes, you will notice there's a portion that is on a strong base as well as a weak acid titration. And this is kind of how it looks like. So, Mr. Leong, looks quite complex, isn't it?
Yes, it does. It's quite intimidating. What does it look like to you?
Yeah, well, it's called a titration curve, but to me, it doesn't look like a curve, you know?
Okay.
Well, what does it look like? It looks like a snake to me, all right?
Okay.
So you can see, I can draw this, you can see there's a tail, and then there's this eye,
Oh, okay. The snake only has one eye. Okay,
The
sure.
other side, the other side.
Oh,
Alright,
the other
you can
side.
see.
Okay.
Alright, so we'll call this a titration snake.
Okay,
alright?
sure.
Okay, let me explain in details. There are a few thought process that everyone, you have to be very clear. Okay, what I do encourage you not to do is to memorize your way through because the permutation are endless. Okay, what is really, really important, I always encourage students to do is to draw a picture to show yourself who is in the burette, who is in the conical flask. Right, so you can see from the reaction over here, we have ethanoic acid reacting with NaOH. Notice they are in equal concentration. So what I have now is I have a certain amount of ethanoic acid. Where is it? It is in my conical flask. And what's happening is I'm adding in NaOH from the burette into the conical flask. Right, so if you can roughly visualize this, what will happen as NaOH begins to enter the solution, I'm expecting my conical flask to be more basic in nature, meaning the pH of the solution should keep increasing, right? Which is something that we see here. You can see that the pH does goes up, but you do notice that the increment is not always the same, right? There's certain parts whereby the increase is exponential. There's certain parts it starts to plateau a little bit, and there's certain parts it goes in a rather linear fashion in terms of the increase, right? So how do we actually think through this, right? The most important thing, guys, is to always focus on the conical flask. It's always about the conical flask. You have to ask yourself that question, what is in the conical flask? And based on what is present in the conical flask, I apply the correct methods based on the situations. Like you can roughly see on this page, right? What are we focusing on? We are focusing on this. What are the species that's left behind? And then each of the species has a particular method to solve for the pH.
Sure. So how about this? Now we're going to focus on what are the species that's present inside the conical flask. We're going to use this simulation to help us to visualize this a little bit better. Shall we do that, Mr. Willem?
Yeah, of course.
Okay. So we're going to take a look at the burette and we're going to see a very huge conical flask going on over here. Okay. Now this conical flask, right, is going to contain 10 moles of my ethanoic acid, right? And of course, my burette is going to be filled up with 12 moles of my NaOH. So you can see 12 NaOH over here. Right? Now, I'm going to start to perform the titration. So that's where I'm going to turn on the tap, right? And you're going to start to see NaOH from here going into the conical flask. So let's see what's going to happen. As the NaOH goes in, you realize that if you pay attention here, one of the ethanoic acid is going to get converted into the salt. Right? So, William, if I look at what is present in the conical flask again, can you share with me what kind of scenarios are you looking at?
Okay, so before we started, right, it was just all ethanoic acid. That means there's only weak acid that's present.
That's right.
But then now the first mole of NaOH has entered the solution, and we know that there's acid-base reaction that has converted into a salt. So if I focus on the conical flask, I see a combination of the weak acid as well as the salt.
Oh, okay.
They are
sure.
conjugate base pair.
That's right.
Therefore, we have a buffer.
Oh, nice. So immediately, the first drop they will add in, the NaOH they add in, is going to immediately create a buffer, right? So of course, if you tell me that if I continue to add in more NaOH, as you can see, the NaOH is going to disappear, and you're going to also see that there's going to be more and more salt being produced. So, William, I remember last time when we discussed buffer, right? There is this concept called a maximum buffer capacity.
Yes.
Can you remind me again, under what scenarios will this happen?
When the ratio of the weak acid and the salt is in a 1:1 ratio,
Right.
we would have achieved maximum buffering capacity.
Oh, that's nice. So that actually means that you're going to have equal amounts of both the acid and the salt. So, William, at this point of time, do you think he has achieved maximum buffer?
No, because if you look at the ratio, I can see that there's 3 moles of a salt
Okay.
and 7 moles of the weak acid.
That's
we
right.
are not at a 1:1 ratio, so I don't expect a maximum buffering capacity to happen just yet.
Okay, so this means that I have to continually add in more NaOH, hoping that at some point of time, the ratio is just going to be 1:1. And we see that over here. You notice that if I've added in 5 moles of NaOH, you're going to see 5 moles of the salt being produced, and what is still left behind is still 5 moles of the ethanoic acid. So at this point of time, we have achieved maximum buffer.
So this is where they will resist the change in the pH the best.
Right.
At this particular moment, we just add in 5 moles of NaOH.
That's right. So the pH change will be the least. Now, if I continue to add on, of course, the buffer is still going to be present, but at some point of time where I've added in 10 moles of NaOH, the last one that I add in is going to perfectly neutralize the final ethanoic acid. Now, at this point of time, if you look at the conical flask, you realize that it is filled full of the salt. and that is where we have achieved this thing called the endpoint.
endpoint, right.
Your indicator is going to switch color, and usually you should stop the titration at this point of time. Now, what happens if you go crazy? Meaning that I'll decide to still turn on the tap and add in more NaOH. Now, look at this again. Before adding in, you realize that there is no more NaOH left. Sorry, there is no more ethanoic acid left in the conical flask. So the moment you start to add in the next NaOH molecule, you realize that there is no acid for you to react with. This means that the NaOH will be unreacted. This is the excess NaOH that's present inside. Now, William, is this a buffer?
Some students are going to mistake this as a buffer because they see again like the two different like a base as well as a salt present. So people will think that it's a buffer. But remember, a buffer must be either a weak acid or a weak base together with a salt. So right now we have NaOH. NaOH is a strong base, right? So this is not a buffer. Okay, important mistake not to make. This is not a buffer, guys.
Okay. So in conclusion, we realize that buffer only occurs at one scenario, and for this particular titration, we realize that it's going to be before the equivalence point. So let's summarize. At the start, in the conical flask, we have the weak acid. Following through, if we add more NaOH, it will form a buffer solution. At some point of time, when we reach the end point, that is only containing the salt. And finally, if you go crazy, add in excess NaOH, it's just simply a scenario where you have excess NaOH, right? It is not a buffer.
Correct.
Okay. Now, shall we go back and take a look at how it correlates to the titration curve?
Yep, so that visualization kind of breaks it down step by step, what happens as we add in NaOH bit by bit. Okay, so what I would do right now is to consolidate that animation into the table over here, right? So what I will do is I will draw again the burette as well as the conical flask. Always make an attempt to draw, it really helps. So you can see I have NaOH and I have ethanoic acid that is present. Okay, so your job is to mentally, at the back of your mind, think through this. What is there before I have started the titration, right? So before anything was added, we only have CH3COOH. That falls into which situation?
So that is going to be a weak acid scenario. That is going to be scenario number 2.
So weak acid, scenario number 2. So remember, every situation has a way to calculate the pH, right? So all you do is you return back to that summary and you just kind of copy whatever that we have mentioned over there. This is the method for us to calculate the pH. So this is before we started the titration, right? So let's say I'm going to add in a little bit of NaOH. Now for consistency, shall we use the same amounts? There are 10 moles inside, right? And I'm going to add in bit by bit. All right, so let's say I've added a certain amount before endpoint. Choose a value.
2 then.
Okay, so let's say I've added 2 moles of NaOH inside the solution, right? But NaOH would have been the limiting reagent at that point. So what is left behind is I have here excess of the unreacted ethanoic acid. And because the NaOH would have reacted away to form a salt, so I do expect these two guys to be present.
Right.
And what situation does I fall into?
Okay, so there are 2 things going on over here. I think there's a weak acid, that is scenario number 2, the weak reagent, as well as a salt, that seems to be scenario number 3. So does that mean that I can just use the formulas from scenario 2 and 3, then perhaps after calculating, I just take the average? Do you think that will work?
Well, it sounds like it. Okay, let's just return back to the situation for them, right? It does sound like, yes, I have a weak acid and I have the salts present at the same time, so it looks like I have 2 different scenarios. But I think it's important that you guys realize there is another scenario, right, which is a buffer. Because I have a conjugate base pair that is present. So the correct way for us to actually solve for this particular situation is to just blindly use the buffer formula, right? And knowing that this is an acidic buffer, so we just throw in the acidic buffer formula, and therefore we can solve for the answer.
Okay, sounds good.
So I think it's really important that students master this particular table itself to know what the situations are and what are the ways to solve for the question.
Yep.
All right. Okay, so let's continue from here. Okay, so after which we will reach endpoint. So endpoint will mean, just nice, we have 10 moles of NaOH that's added into the solution. So you can imagine if 10 moles were to go into the solution, just nice, everything reacts away. What is left behind?
We will only have the salt, and in terms of calculating the pH, this will be scenario number 3. Right? So that is where salt hydrolysis will occur, and of course the methods to calculate the pH will be the same as what you see in the summary table earlier.
So it's important for students to note that this is actually a basic salt, right? So you have to repeat whatever we mentioned, use the Kb expression, press your calculator, and solve for the answer.
So William, I have a question. Can you tell me for this kind, what kind of indicator we'll be using?
Remember, the indicator depends on the nature of the salts, right? So this salt is going to be basic. We will know that the pH is greater than 7. So we must choose one indicator that works in the basic region, right? Which in our case, we have to be choosing phenolphthalein as the choice of the indicator.
That's right.
All right. Okay, so after we go beyond the endpoint, okay, suppose, let's say we add in 12 moles of NaOH. Now it's different because NaOH is going to be the excess reagent. And what's going to be left behind again?
So we realize that NaOH is, there's no more acid for you to react, so it will come in as an excess reagent. So NaOH is definitely going to be present. But of course, before that, you already have the salt, right? The salt will not disappear. It will still be present inside the conical flask.
Is this a buffer?
Good question. So in this case, because you're having a strong reagent, a majority of times when you see there's a strong reagent, you cannot create a buffer. So this is definitely not a buffer. In terms of the formula, this is not situation number 3. Which situation should it be then?
You will always ignore, so the salt itself is going to be insignificant. Let me just write this down, okay, insignificant. So our focus will be only the NaOH that is left behind, and NaOH will become a strong base, right, which means we are returning back to situation number 1. All right, so if it's situation number 1, then we just apply the formula to solve for the answer.
Oh, that's nice.
Yeah, so I think as you can see, what we are trying to do, we're trying to give you guys a thought process, all right? And you can see at all times, where is our focus is always the conical flask, right? Keep asking yourself this question: what are the species that's left behind, right? A picture like this really helps for a start. And once you're very clear what the species left behind, you then move on to apply the correct methods. We haven't done the actual calculations. It will be done in class. This is just an approach, how we actually approach that question. And after which, you can then make sense of the titration curve, all right? Now, as you can see, we have derived that the buffer comes before the endpoint, right? So you could see over here, this particular portion in pink, right? Why is there a plateau? You know this, right? The pH didn't increase linearly as we have expected. You see my line in red. So if there was no buffer, the pH would have gone up straight away. But here there is a plateau because there is a buffer. And what is a buffer trying to do?
It's trying to resist pH changes, and that's where you see a sort of a resistance, right? It is going to be less than linear.
Yes, all right. So every time there is a plateau, there is some sort of like a non-linear increase, then there must be an indication that a buffer is going to be there. Okay, so everyone, you have to take note that the buffer comes before the endpoint in this titration. Right, at certain critical levels, so in this case, at just nice 25.00 cm cubed, we have reached the equivalence point. Right, so the equivalence point is where you see an exponential increase in the pH because you were changing from a buffer towards only salts left situation, and then just add one more drop later, the whole thing is going to change again now to a basic solution. So you will see this like vertical region that stands for an exponential increase in pH that also corresponds to a change in situations. Right, then after which you can see that the pH is increasing in a linear fashion simply because there is no buffer that is formed. And that explains how the titration curve is being drawn.
That's nice. So one of the things that you'll notice is that we have this idea called a maximum buffer capacity. And if you have gone through your school lecture, most of the time they'll just tell you that, oh, if you have a buffer that is before the equivalence point, the volume will definitely be half of that of the equivalence point. So why is that really true? Honestly, maybe your school didn't really do a very good job in explaining that. So I think we will try our best to explain it right now. Okay, so we're going to start off with the same kind of explanation again. Let's say I'm going to start off with 10 moles of ethanoic acid. And remember, what is the objective, right? Is to achieve the maximum buffer. And William, remind me again, how do you get a maximum buffer solution?
You need a ratio to be 1:1, the weak acid as well as the salts to be in a 1:1 ratio.
Right, so once again, we are going to focus back onto the conical flask. So I'm going to quickly draw a diagram again. You have a burette, which is your NaOH, and as well as your conical flask, which you're going to have your ethanoic acid. Right, so once again, put your eyes into your conical flask, look at your conical flask, and we want to achieve equal amounts of the ethanoic acid as well as the salt over here. So I hope that these two will be the same number. Now, William, your job now is to do this. I want you to think about how much of the NaOH should you be adding in such that at the end of the day, in the conical flask, these two numbers are equal. Can you make a guess?
Okay, so I'm looking at the conical flask.
Yes.
All right, I know that at the end of the reaction, the attenuic acid must be there.
Okay.
So attenuic acid must be in excess no matter what.
Okay.
Okay. So NaOH being the limiting reagent, right? I'm going to predict that we will need 5 moles.
Okay.
Let's try 5.
Okay, sure. So since you say that NaOH is adding in as a limiting reagent, it means that all the NaOH must be used up.
Yep.
Now at this point of time, you tell me that 5 moles has been used up, which means that 5 moles of the acid will react. And how much are you left with?
5.
5. And all these NaOH we have converted into the salt. That will mean that you will also get 5 moles of the salt. And yes, very good. Very smart guess. You will get the same amount of ethanoic acid as well as the salt itself. Now, what you notice over here is what the William add in, this 5 moles over here is actually going to be half of what the initial amount of ethanoic acid is. So this gives us a very important conclusion over here, that if your buffer region occurs before the equivalence point, then your maximum buffer will always have the volume half of that of the equivalence point.
Yep, we can actually mark it out for them on the titration curve itself. Okay, so if we return back to the previous page, let's mark out for them where's NBC.
So this is the equivalence volume. The half of the equivalence volume is going to be here, which means that if I dot it up onto the curve, this part over here will be known as the maximum buffer capacity. So would you want to summarize this for us?
Yep, okay, so what we have done, as I consolidate one more time, is to really draw the conical flask as well as the Buret, look for where is the buffer. It can't be memorized, right? It has to be derived using your focus on the conical flask, right? Ask yourself what are the species that's left behind, then use the correct method to calculate the pH. Once that is done, you will be able to draw the titration curve. It's a skill that we will share in more details when we return back to class at the end of this week. Right, and that is only one of the 4 titration curves. So the other 3 is going to be covered in class, right? So we will do that in class together with the rest of the students.
All right.
All right. So yeah,
See you
do it
guys.
up. See you guys. Okay. Bye-bye.
Bye.